Okay, good morning. Like you know, my name is René Schneider. I come from Switzerland. I'm basically a surveyor. I have more than 50 years experience by Leica. And yeah, in Switzerland is known that you work first by Leica. And now I have my own company, Happy Monitoring, where I have created the first RTK-based monitoring system in the world. I show you a little bit the history and what this system can do, especially also with artificial intelligence. The beginning of a new era. For us, it was the beginning of a new era because nobody knows in the beginning what is the result that we will have in the future. We began in 2018 with the development of Happy Monitoring. That was in this moment only with GPS and GLONASS. And in 2017, we have changed the algorithm because it's coming Galileo. And now we have the full constellation with Beidou B3. I will show you the evolution of the systems. We have We have first GPS, GLONASS, Galileo, Beidou. What we have saw when we have begun to develop an RTK-based monitoring system, not post-processing, we saw that Galileo brings a lot of quality in horizontal precision. But the height was in about 3 to 5 millimeters. It was not so perfect. Then it's coming Beidou and Beidou B3. And with this system, we can now really go in 1 millimeter precision in height. You will see in the examples and the measurements that we are monitoring that we make in Hong Kong, that we can achieve that. It is important to understand the difference between sensors. Most of the known sensors work in the old way. They have basically GPS, like the best system that gives you the coordinate. And GLONASS, Galileo, Beidou is nice to have. You can check that when you have a GPS sensor, you turn off GPS, you will see that it's very difficult to have a fix. On the other side is technology from South, also now from other companies, that you can fix alone with Beidou, alone with Galileo, alone with GLONASS, and alone with GPS. That means this new technology of sensors use the best satellites in this moment to create the highest precision. And that gives us completely new possibilities to work on the sensor side with RTK. You can check that also in Hong Kong. It's really difficult in Hong Kong. We have the high buildings. You will see that sensors on new technology measure a lot more points and more precise than GPS-based sensors. So that is one thing that helped us a lot to achieve this precision that we now have, that we have these sensors. They are completely open to all systems. What we need for Happy Monitoring is simple. We need power, we need internet, because it's RTK, so we need internet. We must see a little bit of sky, or without that it doesn't work. And we need a geologist or an engineer that help us to determine the position of the base station. Where is a fixed point that we can use? How we can do that? I repeat, first of all, we use only RTK coordinates. There's no RINEX, no raw data registration in our system. We have an intelligent algorithm for the measurement correction. You can imagine we receive every 5 seconds a coordinate. In a daytime, we find about 18,000 coordinates. And we must use a statistic model of that. That means algorithm, we detect a normal wave on a point, on every single point. So that permits us to eliminate bad measurements, to detect good measurements and make a mean of that. And with the artificial intelligence that is now in the version 5 completely integrated, it's the algorithm by himself that decide in which direction he will go. Before, it was limitations that we give on the statistics of the point. Now it's the whole process is free open. So we can detect also very fast measurements and very big measurements, movements. Excuse me. And the high data transmission rate, like I have said, every 5 seconds we receive a coordinate on our server. I begin with a project because this project was the key that the Technical University of Munich have decided to make an accuracy test of our system. You must see, when normally I talk about happy monitoring, RTK monitoring, the people said to me that is not possible. RTK is 1-2 centimeter. What do you talk about? That is not possible. So I will show you the results of the University of Munich about the test of our system. And that begins on this mountain. This mountain is exactly the cross here. It's the border between Germany and Austria. And like you see, this is falling down. It's in about 600,000 cubic meter of rock. That is the most measured mountain in Europe. On this mountain, there are scanners, total stations, crack meters, pisto, the whole year. Because we know that it's falling down in the next years. And so that is permanently 24 hours controlled. In this case, the professor of geology from the University of Munich came to us and said, look, we know very good this distance, what this made. We don't know that it's only this part that is moving, or it's moving also this part. Because it's only a relative measurement on the peak of the mountain. So we have put one sensor here and one sensor on this side. And to show you, and that is the system, the result, that is one sensor on the mountain, and the base station is here in the valley. We measure 5 kilometers distance and 1,500 meters of height difference on the mountain. The astrophysicians here inside knows that it's very, very difficult, a so big height difference with GPS, because we have troposphere effects that are very strong. And we have begun to measure 1 year, and the results was in about 1.2 millimeters of precision in position in 2 days calculation. Every 2 days, one result. And then the Technical University of Munich, Professor Holz is the professor for geodesy, is coming and said, we like to test that because it's impossible what you measure. And so they have begun a test of 6 months of measurement. And that is important now. That is in perfect conditions. Horizontal baseline, totally open sky. That's the best achievable precision that we can have, that you see now. Because when you think in Hong Kong, is perhaps one of the most difficult regions to measure, because the ionosphere here is really have a high noise. The test that they made was in 3 steps. Step A, achievable coordinate precision of stationary rover. Then absolute distance between 2 rovers, and the absolute precision in movement when the point is moving. So they have tested in different baseline lengths, and they have tested in different time, the calculation from 1 hour to 24-hour data. And that it was cold temperature. Yeah, that was in the winter. Now, first, a simple coordinate. How precise I can determine coordinate. And you see here, every hour a solution and every day a solution. That is important to understand. How faster we measure, how more noise we have inside. And this is the distance from 5 to 20 kilometers. Baseline, base, row. You can see here that we achieve in, it was 6 to 23 days. We have an error that's in about 1.5 millimeter or 20 kilometers. 5 kilometers we are down, under 1 mm. Then they have tested 2 rovers. These 2 pillars, this is the most precise distance in Europe. That was measured from 3 universities together. They know the precision in 1/1000th of a millimeter. And so they put our sensors, 2 rovers here, and that is the distance. I show you this graphic is better. Then they have tested with a base on 1 kilometer and a base on 10 kilometers away from these 2 pillars. You can see with 1 kilometer, we have 1/1000th of a millimeter, and in height 1 millimeter. And that is the effect of Beidou. Before, this is not possible. With the new Beidou satellites, we have now here on 10 kilometers, we are also at 1 millimeter. That is for the settlement measurement, that's absolutely important that not only the position is good, but also the height. Because when someone is a surveyor, you know, 1 millimeter, 2 millimeters, more it's not possible. It's physically not possible to make an interpretation of 1 or 2 millimeters. And then they have set up a rover. You see, it's very cold. And then with a micrometer stage, that they can move the sensor up, down, left, right, and all the directions. And so in this graph, we see that the measurements are falling into 1-2 millimeters exactly the changings that was made on the micrometer stage. Something that is because our algorithm is like this. When you have a very fast changement of 5-6 millimeters, you will have for 1 hour no data. Because the artificial intelligence must understand what happens, in which direction, because can we go up and go down. So he liked to find out exactly what happens on the point. And you see here the average residuals are plain 0.3 millimeter high, 0.9 millimeter. In movement, that is then for landslides on the measurement that we make here for the CDD. And here is a resume about what we can achieve. 1 kilometer baseline, you see we are in about 1 millimeter in height and less than 1 millimeter in position. On 10 kilometers, we are in about 2.53 millimeters in height and less than 2 millimeters in position. These are data from the university, not from us. They make the test. And when you think you have to do a double high precision leveling, 10 kilometers, forward and back, you will never have this result. This is better than your leveling. Here, the Hochvogel, that is the base station. I love this picture because it gives an imagine how far away is the base station and where we measure. We measure here on the top with the 2 rovers. Here is a graphical design about the distance, height difference. You can see here the solutions from the two rovers. One rover is stable, is in about 2 millimeters, and the other rover is going in the direction where the landslide is also measured by the other sensors. Important is the difference between the sensors is the position is much higher than the absolute position of the point. When we take the distance between the two rovers, it's less than a half a millimeter between the total station and our measurement. The absolute positioning is in about 2 millimeters. Here you see the comparison to the network. What they measure with all the sensors is, yeah, with scanner and all what they have, and what is our machine. It's quite the same. So we can measure something on a long distance that normally is impossible to go on the mountain with that. And the conclusion from the university is that this permanent monitoring system increased the accuracy. Depends on how long we can measure. And the accuracy also depends on the distance between base and rover. But normally for 2 kilometers, we are below 1 millimeter, 3D. And that is really a new era of monitoring. For the absolute positioning on the hook, they will do a next evaluation together with the astrophysicians, because there is they need more information why it works. Because when you read the books is written that doesn't work. Well, not possible, but now we measure 3 years, and in 3 years it's perfect. So they will do another test about especially this mountain. And now some cases, what we do. This one is nice because perhaps you know this mountain in Switzerland is here. It's the most famous mountain in Switzerland. And here we have a landslide, but the landslide is in the wood. The point is here. With these new sensors, with this new technology, you can also put the sensor in the wood. We need in this case, for example, for one coordinates 2 days, because it's clear that when we have wind, the trees are moving, so the system needs more time. But we can detect also in these difficult conditions, or here also the same. We can achieve in about 1 to 1.5 millimeters of precision, 3-dimensional. This is the height. You see how smooth the height is coming down. Will mean the slide is like this, go down. Then another critical project, this is a highway bridge in Austria, where the engineer don't like to put the sensor over the bridge. He needs to monitor the pillar. So we must make this construction, and half the sky is cut away by the bridge. Especially in Europe, we have the satellite more in the south side, in the north side less. So problematic is this point here. This on the north side. I have less satellite and half the sky is away. And also here now we have version 4, like calculation. That means it's a high value of artificial intelligence inside. And we are in about 2 millimeters, 3-dimensional, under the bridge. That can help you here in Hong Kong, that we have the problem of the buildings. You don't need for monitoring all the sky ops. We can also, under difficult conditions, find a solution when we have time. It's not for fast monitoring. It's permanent, long-term monitoring. Then monitoring that is also in a in Europe a high-risk project. These dams, only in Austria, are in about 70,000 of them. That is when in the mountain is high water, rainfall, and you have a landslide that blocks the slide. And I think you will have that also here in Asia or surely also in Hong Kong. And these walls are to monitor, because when this is falling down, the village on the top, that will be destroyed. They are all for the safety. We have these dams on the water flows from the mountains. And normally very difficult conditions. There is in the mountain, in a valley, you have things, and you have normally no internet. That is another problem. Doesn't work. Yes. Yes. Now we come nearer to Asia. To you, it is Jakarta in Indonesia. Perhaps you have heard about the problem that Jakarta is going down into the sea, the subsidence. And here we have tested in about 3 years now, because problem of Jakarta is the distance. That is, the whole city is going down. And the next fixed point is on 50 kilometers. So we have adopted here a technology that we have a base station in the subsidence area, and we have a 0 point outside. Then we use the results like leveling. This measurement is the back side, and this measurement is floor. So we can determine the height difference between the 0 point and this point 0. And in this case, in every port, the biggest problem is interference. When you work on a port, the ISF can talk about that, and the CED also. You have so much radios, Doppler radios from the ships that disturb the satellite signals. So you have to change the technology totally in these regions to achieve high precision results. That was in the last 2 years, I think, the biggest work that we have done for Jakarta and for Hong Kong to find a solution on these interferences near to a port. Here you see that is a sensor, and housing on top are 4 sensors. There are 4 inside. One tube going 1 meter into the ground, one tube 100, and one tube 200 meters into the ground. That is to detect where finish the subsidence. How depth is the fixed soil, and where we have the subsidence area. And from these houses now they build 2 in every 100 biggest cities in Indonesia, where then is 4 sensors up, and we measure the different depth for they like to do a drainage of the city in this case. Now we are in Hong Kong. When we have begun with YSF, the first project was trunk road, a bridge monitoring, and it works perfect. It was so nice. We are all lucky, results are good. And we said, okay, we go ahead. That is a picture of the trunk road. But then we have begun to make monitoring here. And here the interference is extreme. I never saw something like that. That is that the measurements go up 6 centimeters, come down 7 centimeters. Make like this. When Chinese telecom turn on the antenna, then make woof. go up and down. So here we have begun, together with YSF, to develop a solution especially for this region. And here without artificial intelligence is impossible. Here you are in centimeters, never in millimeters. Then we have found the solution for that here. And then it comes to monitoring from the breakwater. That is our last evolution of the system. We have 5 sensors on the breakwater. And 2 weeks ago, the tunnel boring machine is going under this breakwater. You can see that one tunnel boring machine now is, I think, here, and the other one in 3 weeks will come. 3 weeks is right. In 3 weeks will come in here. And the chief surveyor from CEDD had said to me that a normal measurement here with a total station, something like that, is impossible. You don't achieve the precision because reflection from the sea is too far away. So the only system that have monitored in this case was Happy Monitoring. It was also a big responsibility. And you see here the results. Should I go back? Point 1 is outside of the TDM. Point 2 and 3 is directly under the TDM. Point 4 and 5 is outside of the TDM. And you see here the results. You see that when the TDM is coming, point 1, 4, and 5 stable into 1, 2 millimeter in the height. That is only the height. Point 2 and 3 goes down. And the point 3 goes faster down than point 2, and point 2 is following. When you go back, that was exactly what the engineers expected. They expected 2 centimeters of settlement in this specific place. And we are here in 1.9, 1.8 centimeter. And yesterday, the chief of CEDD said to me, "You makes me happy." And that was really a big compliment for us, because it's one of the most difficult monitoring that we have made in these conditions. And we can show that the systems react with a delay of about 10 hours directly in real time on a building site. And so that is Happy Monitoring. What we do, what we can do, we can go long distance, high precision, especially settlement. Now the height we can monitor in millimeter precision. So, thank you very much. That is all.